Hello students. Today we will start our discussion with something that is related to the structural properties of single polymer chains. So in last few classes in our discussion regarding biomaterials, we have started discussing with polymers as polymers are the most abundant kind of biomaterials that we find. So understanding these basic fundamental materials which are basically collections or simply chains made of units which we call monomers is very important. So in the last few classes what we did is we first understood what polymers are, we defined molecular weights and saw that how these molecular weights could be very much diverse when you perform a polymerization reaction, and from there we defined different ways. We learned about different ways of defining these molecular weights. We also learned about this quantity called polydispersity that tells you that how divergent the lengths are from the mean length. We also talked about the forces involved in this context in the last class, and now it is time that we talk about the structural properties of these polymer chains. Now, long chain macromolecules like polymers and also proteins, they can assume enormous number of different conformations. So by conformation, I mean structures. So as they are long chains, right? So you can imagine that they can have different kind of structures depending on the solvent also. Sometimes they could be like this, that is they are completely open. Sometimes they are a little bit coiled up like this example, right? And sometimes they are absolutely very highly coiled up depending on the kind of material, the kind of solvent they are in. So there are also different kind of other factors involved in this, like the rotation of their chemical bonds, how flexible or how rigid the chemical bonds are. In addition to that, the nature of solvent medium, as I was saying, that in which solvent they are present, and external constraints like pressure, temperature, ionic environment, sometimes electromagnetic field also, etc. Right? They can have this profound effect on how different conformations can be achieved. So in a given system of polymers, it is reasonable to describe the size of these polymers in terms of that polydispersity, right? That how different they are in terms of their length. Now in this chapter, what we will be concerned with is like in an equilibrium state, how do you measure these characteristics lengths, right? So if you have, just imagine that you have a polymer with n number of monomers present in it, what could be the physical size, right, of this chain? What could be the spread of these chains? So there are certain models, certain ways that we talk about these conformations, and these two are very popular models called freely jointed models and random flight models. We'll talk about both these models in this particular chapter. So before we go into the discussion of single molecule behavior of polymers, let us introduce certain concepts regarding characteristics chain size, right? So suppose you have a certain polymer present in a just a minute. Yeah. So a certain polymer present in a solvent. So it could be assumed as a linear flexible chain, right? So polymer could be assumed as a linear flexible chain of beads. So you can consider a bead, and with that a little bit of bond, then another bead, then another bond, and then another bead, right? So you can consider it to be a structure like this. So each of these beads could be your monomers, and each of these lines that I am drawing, the threads I am drawing in between, are basically the bonds holding hands that these particular monomers are joined together, right? So this particular structure that we assume, that we consider, or the polymer takes inside any solvent, they can be considered as a sequence of beads, right? Sequence of beads on a string. So they could be considered as a sequence of beads on a string, and they can assume any particular conformation that you can think of. So these beads representing the monomers, and the length between these two bits, right? The length between these two bits can be considered as the monomer length. You can consider it to be the monomer length. So let us further simplify this system, and let us consider this particular polymer chain that we are considering in terms of geometric structure. So you remember a quantity called radius of gyration. So radius of gyration is basically something that when you consider that you have any shape present and any 3D shape present somewhere, and it has a certain degrees of freedom to rotate around it. So from there we define something called moment of inertia, and you have learned these things before in your school days, so I am not going into detail of that what moment of inertia is. But radius of gyration is something that is related to a standard size, a characteristic size of a material. So that is one way of talking about these chains, right? So in terms of these chains, we will define certain quantities like this, like radius of gyration, hydrodynamic radius, which is sometimes denoted as RH, right? So let us just remember the notations. Rg is a standard notation for radius of gyration, RH a standard notation for hydrodynamic radius. I will define all these quantities. Dry radius Rd, and contour length of the chain Rm. So these are basically the four basic lengths associated with any polymer chain. So what are these quantities? So let us consider that we have a polymer chain. So I was drawing this polymer chain. Let me draw it a little bit longer. Let us consider that this is a polymer chain, and this is inside a certain solvent, and this is the conformation that it has achieved right now, right? So this is the polymer chain. So let us consider there are n number of monomer units in this, and each of these monomers have a length of B0. So B0 is being considered as the size of each of these monomers, right? So n number of monomer units, B0 is the size of each of them. Okay. Now if you consider this length, right, and this is not directly related to B0, NB0, right? Because NB0 would be the condition when it is just as if it's a very rigid stick. Then only you can have N times B0, isn't it? So N times B0 would be when the bonds are all straight and they are all lying side by side, and you have stretched the polymer such that it is almost in form of a stick. In that case, you can call the length as NB0. But otherwise, this particular size, if I want to relate a size with this shape that it has assumed, we don't really know how to relate it with N or B0. And thus we need these quantities. Like radius of gyration, hydrodynamic radius, dry radius, or the contour length to talk about the size in terms of when it is inside a solvent. Okay. So the first and foremost quantity that we define is radius of gyration. Radius of gyration is defined like this. So radius of gyration is nothing but it tells you that if there is a center of mass in any solid body that you can assume, right? Any arbitrary shape that you can assume, there is always a center of mass associated with it, right? How do you calculate the center of mass? You take each of the particles and see that how far they are from this center of mass, and when you collect everything together, it will seem that it is basically a point mass instead of this arbitrary shape. This particular 3D object is basically, you can consider that all its mass is concentrated on its center of mass, right? So physically, radius of gyration accounts for that how the mass of the object is distributed about its center of mass. How the mass is distributed about its center of mass, right? So if it is a round shaped object like this, right? If it is a square object like this, if it is a rod like this, right? So for all of these different shapes, the center of mass will be somewhere here, and radius of gyration will tell you that how far away or how close to the center of mass the entire mass of the body is distributed. What is the shape? So it accounts for the shape. It kind of accounts for the shape, right? So this is how we define center of mass. What are these quantities? It tells you Rg square is the center of mass square, and it takes an average over all the n number of particles in it. So in case of our polymers, here the particles, we are not going to each and every single molecule in the system, but we are talking about each and every monomer. So we average over n square. So this is the definition of radius of gyration. Let us come to the next one. The next one is hydrodynamic radius. Hydrodynamics radius is basically derived from something called Stokes-Einstein relation. So this basically tells you that if you have a certain any shape, any particular shape of a 3D object, and it is passing through a certain liquid which has a translational diffusion coefficient of D. So suppose you have a very dense material like glycerin, right, liquid, or a very very comfortable material like water, right, it's not very dense. So in that case, how fast or how slow that particular object will pass through that liquid, and will it depend on its shape? Obviously it will depend on its shape, right? So if you just imagine that you have a column of glycerin present inside your laboratory, a long column, right, 1 meter, 2 meter long column, and you are dropping several different shapes, say round shape, a square shape, a shape which is like a rod. Let us take these three same examples. How easy or how difficult it is for these items to pass through this column of glycerin, right? So Stokes-Einstein equation talks about diffusion coefficient, and from there also you can have a certain estimation that how big or how small this particular system is that is dropping through the material. So here it depends on several different factors like temperature of the solvent. This capital T is temperature, right? Eta 0 and Kb is basically eta 0 is the solvent's viscosity. I was talking about that how dense this liquid is, right? So this is basically the viscosity that measures that how dense this particular liquid is. Kb is Boltzmann's constant, and Rh is equivalent radius of a sphere that diffuses through this particular material and measures a diffusion coefficient of capital D. So these two quantities that we have defined, Rh, that is hydrodynamic radius, and Rg, that is radius of gyration, both are basically, you can figure it out using experiments, right? They are experimentally determinable because there are several moment of inertia models, moment of inertia experiments from which you can draw an explicit conclusion about how your Rg would look like, right? And you can have definitely measure it. You remember, if you don't remember, you just ruffle through some of your school days books, and you can see that this is how it will look like for different kind of shapes, for sphere of a radius, for thin rod of length L, for a thin disc of radius R. This could be the different shapes that are present, right? So for different shapes, moment of inertia is different, and from there you can figure out what are the radius of gyration in those cases. So in terms of these two parameters, Rg and Rh, we can have a certain estimation of how these quantities can be measured, right? So let us talk about the third quantity, Rm. Rm is the contour length, and Rm is basically NB0. So I was talking about this polymer chain in the previous slide. When the polymer chain is perfectly stretched, you have B0 each monomer's length and n number of monomers present there. If you stretch it, then Rm will be the contour length, that particular length, n into B0, right? So if a polymer chain is stretched, pulling its end completely apart, then you have the maximum, it's kind of the maximum length that the polymer can achieve, right? So it is called contour length. Rm is the notation for that. And finally, let us talk about dry radius. Dry radius is something that is basically when you consider for any polymer lying inside some water or some other liquid, then R H, that is the hydration, hydration layer. So there is always this hydrodynamic radius will have a hydration layer, or the layer of the liquid present on top of it, right? So RH will be given by RD, that is the dry radius, RD plus D. So D, this small d is basically the thickness of the solvent attached to it, right? So you will have always, if you have a polymer present inside a liquid, there will be always a small thickness of water attached to it, right? So that is called hydration sheath. That is also sometimes called hydration sheath. So this D is the width of that hydration sheath. So great. So we have defined several different quantities which could be characteristically give us some idea about how this polymer's length could be measured, right? These are some general characteristics lengths. So in case of a polymer, how will we estimate this quantity, say Rg? Let us define, I want to figure out that what is this length Rg in terms of a polymer chain. Or can we have a more fundamental way of defining that if I have a polymer chain spread out like this, so this is one end and say this is one end. So can I have a concrete measure of what is the more or less the shape that it is holding, or what is the more or less the size that the polymer is occupying inside the liquid? So for that we have a very solid model, and the first one, which is a simple one, is called a freely jointed chain model. So let us come to discuss about this freely jointed chain model. So in freely jointed chain model, we will use the concepts of whatever concepts we have defined so far, like Rg and hydration and all. We will take them together and we will try to define something particularly related to a polymer chain, right? So let us consider a polymer chain with the same definition, that we have n units of monomers and each have a size of B0. By size I mean length. So each of them have a length of B0, right? So these monomer units are capable of random orientation with respect to each other. So that suppose this is one monomer unit and the next monomer unit can be anywhere, right? The next monomer unit can be anywhere. The fourth one can be anywhere. So there is no restriction that which way they can be and which way they cannot. So they can have any particular orientation which will give rise to a shape like this, right? So this is the kind of shape that we are assuming. So what we are doing here, I drew these small vectors here, right? What do I mean by these vectors? So these vectors are basically telling you that how much the first monomer is long and what is its orientation. So I am taking each of these monomers and describing them in terms of something which we call bond vectors. So bond vectors are nothing but you have this polymer chain, say the orientation of polymer chain is something like this, right? This is the orientation of polymer chain, and you break it down in a piecewise linear manner, right? Piecewise linear manner you break it down, and you consider that up to this point is one vector. This is the first monomer. Up to this is the second monomer. Up to this is the third monomer. Up to this is the fourth monomer, and so on. You make it a piecewise linear distribution of small bond vectors which we call R1, R2, R3, Rn, because there are n number of them, so there would be Rn, right? So note that all of them have equal length. Note that all of them Ri ka, if you take a Ri of modulus of Ri, length of Ri, all of them would be equal to B0 for all I, because they are all same monomers we are considering right now, right? So all of them are of same length. We can alternatively do this, that we can, if it is something like that, then we can also consider that, specify the position of all these n monomers, and we can also take it in terms of some position vectors. Let me tell you what I mean by position vectors. Let us consider that this is the chain that we are just drawing, R1, R2, R3, Rn, and like that, right? So we consider this is our origin, and in terms of the origin also we can figure out the position of each of the monomers. So this is R0, the first point is R0, say, where the first monomer's tail starts, and this is the first monomer's head, right? So if you join this point with the origin, and this would be a vector, this vector is going to be your R1, capital R1. So I hope you understand what is the difference between capital R1 and small r1. Capital R1 is the position vector of the head of the first monomer. R0 is the position of the tail of the first monomer. Now first monomer's head and second monomer's tail are at the same position. So R1 will do the job as R0 for the second monomer, and you can draw another vector from this point to your origin. From this point to this point, you join it like this. This is going to be the vector. You join it, and this is your R2, right? This is your R2. So this is how you define them in terms of position vector. Now you all remember the vector addition rules, right? So vector addition rule, if you use, you will see that, what do you see? R0, this is R0 plus small r1 is equal to capital R1. So let me write it here, R0 plus small r1 plus small r1 is equal to capital R1, using the triangular addition rule of vector. Okay? So if this is true, then you can write small r1 is equal to capital R1 minus R0, right? Small r1 is equal to capital R1 minus R0. Similarly, what will be small r2? Small r2 will be capital R2 minus R1. Capital R2 minus capital R1. So in general, you can write that small rn is going to be equal to capital Rn minus capital Rn minus 1. So you can write that small rn is going to be equal to capital Rn, and this is very important, this is going to be equal to capital Rn minus capital R n minus 1. Okay, great. So this is true for all n. This is true for all n 1, 2, 3, 4 up to capital N. That is the total number of monomers we have, right? So that means we defined this entire chain in terms of some vectors, right? And vector addition is something that we are very comfortable with. So now if I want to define a quantity, and this quantity is called end-to-end length. So end-to-end length of a polymer. How do we define it? This is directly related to the polymer, as I was talking about. So end-to-end length simply means that from this point to this point, what is the length? Now remember that this is not RM. This is not your contour length, because contour length will be when this entire chain is spread out, and that length is obviously going to be more than this end-to-end length, which we define by RE. RE is the end-to-end length that tells you that where the head of the final monomer is and where the tail of the first monomer is. That is your end-to-end length, right? End-to-end length is RE, which is defined by this particular vector that is drawn here, this particular vector. Okay. So what is this thing? So if you look at the position vectors, this is basically Rn minus R naught, right? So Rn minus R naught, just use the triangular law of vector and you can find out that R0 plus Re is equal to Rn. R0 is this, right? Plus Re, direction is this way, so Re is equal to Rn, and from there you get Rn minus R0. Now you can one by one replace each of these quantities. What is Rn, and then what is Rn minus 1, and then what is Rn minus 2, and so on. You go on replacing them and you will finally get, I am giving it this to as a home task. You just try it out and check that this is nothing but a sum over Rn vector, and this is important. It is sum over Rn vector, right? Now Rn has a random orientation. As I told you that each of these vectors have a complete freedom and they could be oriented anyway. It does not depend on the previous vector as well, that which way the final vector will be oriented. This is the simplest model, the freely jointed chain model, that assumes that these vectors could be in any possible direction. So if you add on a few random oriented vectors, what will you get? Randomly oriented vectors mean you will get 0, right? So Rn average is 0. If you add all the random direction vectors, just assume forces. Forces are vectors, right? Just assume that you have random direction forces. So if all of them are in the random direction, finally no force will be effective, right? Similarly here also, if all the Rn's are in random direction, then the sum over them is always going to result as 0, leading to Re equal to 0. So this is like becoming something that we define, but it does not mean anything. But what we should do is that we should not calculate just Re, but what we should do is calculate something that is the mean square value. And you know what mean square value is, right? So what we will do, we will square Re and we will take average of that, right? Mean square means you take a mean of the square, right? So you take Re, you square it and you then take a mean. So that basically gives you Rn minus R naught square. Rn minus R naught square average. So this is not going to be 0 because here you have them squared. So let me just quickly show you how the calculation will go through. You just try it out once. I am just keeping the screen fixed for a while. You just try it out once. So what we do is that you take Re square and then you consider that there are two indices like R1, R2, R2, R3, R3, R4, something like that, and you take a dot product of them and then you are doing an average, right? So Re square average basically means Rn dot Rm average, and from there you get Rn square from the first term, right? And then you get 2 Rn Rm. So 2 into Rn and Rm, because n is not equal to m and all vectors, I mean if n is not equal to m, then they are randomly oriented. So if you have randomly oriented vectors, then you will have their dot product as 0. So the only thing that is left there is the ones that are n equal to m. So if you look at this quantity Rn dot Rm, there two things can happen, right? N is equal to m or n not is equal to m. So this is the quantity representing n not equal to m, and this is the quantity representing n equal to m. So if you have n equal to m, then those terms survive and rest of them go to 0. So when n is equal to m, you get Rn square's average. That means Rn square is B0 square, and you sum it over for n times, so n times B0 square. This is a very, very important result, that Re mod square average is n B0 square. That means that is telling you something really important, that the end to end length cannot be whatever you want. It is not that you have a polymer and its end-to-end length can be very small or very large. It has a certain measure. It has a certain statistical measure. It is proportional to n to the power half. What is n? The number of monomers present there. So the end-to-end length is basically proportional to n to the power half. It is called an universal scaling relation. It is very interesting relation that there is a direct relation between the end-to-end length and the number of monomers present there, and you know that the number of monomers directly relates to its molecular weight. That means the end-to-end length and the mass of the chain is directly related via a scaling factor of half. So what you have on top here is called a scaling factor, and this is an universal scaling relation that both these quantities n and m directly reflect the size that you see of a chain inside a solvent, right? So this is where we stop today. Go through this discussion and we will continue with the random flight chain model in the next class. Thank you.